Hello everyone, welcome back to lecture 2 of Cycles and Residence Time in week 9 of the Blue Planet. Today we'll explore the carbon cycle a little further and what happens when we perturb it. So that's captured here in our learning objectives where we're going to apply the knowledge of residence time to Earth's major carbon cycle reservoirs and the fluxes between them to predict the response to a carbon cycle perturbation. So some of the key questions that we'll be addressing today and later in the week are these. What happens if we stop emitting carbon dioxide into the atmosphere? How long will anthropogenic CO2 remain in the atmosphere? Where would the excess CO2 go? We're also going to explore some feedback mechanisms and the difference between positive feedbacks and negative feedbacks. But the big question of the day is, with this trajectory of CO2 increasing from about 300 years ago through to the present, what is going to happen to that trajectory if we stop emitting carbon dioxide into the atmosphere? Well, the starting point for doing this, just like the hydrological cycle, is to take a closer look at the carbon cycle. And so here we have a diagram of the major reservoirs in the carbon cycle and also the fluxes between those reservoirs. Now this diagram is complicated a little bit by the fact that it has both black and red arrows on it, and it has black numbers as well as red numbers which represent the carbon stocks in the reservoirs. So the important thing firstly is that the black numbers and the black arrows represent the pre-industrial reservoir sizes in gigatons of carbon, so that's billions of tons of carbon, and the fluxes of carbon in gigatons of carbon per year between the reservoirs. The red numbers are the changes in the reservoir sizes and fluxes due to anthropogenic carbon emissions, CO2 emissions. So they're the additional amounts of carbon that are in the reservoirs that have been put there since pre-industrial times, and the red arrows represent the increases in the fluxes. So for example, here we have the flux from the atmosphere into the ocean. It was 70 gigatons per year in pre-industrial times, and now there's an additional 22.2 gigatons per year moving from the atmosphere into the ocean. So a total of 92.2 gigatons of carbon per year moved from the atmosphere into the ocean. So with those numbers in hand, let's quickly have a look at the size of the reservoirs that are indicated here. So here we have the atmosphere at the top, and there are about 600 gigatons, or there was about 600 gigatons of carbon in the atmosphere in pre-industrial times, and we've since added an additional 165 gigatons of carbon. I'll show you that's actually quite a lot higher than that, because this diagram actually relates to numbers back in the mid-1990s. So here we have the atmosphere. Then we have, over here, we have what's called vegetation, soil, and detritus. This would be otherwise known as the terrestrial biosphere. And that has this number here of 2,300 gigatons of carbon. So it's about 2.5 times, it's about 4 times the size of the atmosphere, the terrestrial biosphere. And then we have the surface ocean, and it's divided, so the ocean itself is actually divided up into the surface ocean and the deep ocean, or deeper ocean. And when we do the oceans, when we look at the oceans next week, that'll become apparent to you why we divide the ocean up into these two parts. But the surface ocean has had about 900 gigatons of carbon in pre-industrial times, and that's gone up slightly. due to anthropogenic carbon emissions. And if you have a look down here, the deep ocean, or the intermediate and deep ocean, has 37,100 gigatons of carbon, and it's had a very relatively small amount added to it since pre-industrial times. But this is by far the vast mass of carbon that's within the carbon cycle resides in the ocean, and in particular in the deep ocean. There are a couple of other smaller reservoirs noted here, such as the marine biota, which is relatively small at 3 gigatons. And there are these surface sediments of the ocean which react with the deep ocean water, and there are about 150 gigatons of carbon in that water. Now, the other notable reservoir here is fossil fuels. So what this is saying is that the estimates at the time in the mid-1990s were that 3,700 gigatons of carbon was available in fossil fuels, that's coal and oil and gas. That was available to be burnt and emitted into the atmosphere as carbon dioxide. And as of this particular time, there had been 244 gigatons of carbon burnt of that fossil fuel and emitted into the atmosphere. Now, in addition to that, that's not the only anthropogenic source of carbon emissions into the atmosphere. There is also our impact on the terrestrial biosphere, where we cut down forests and then degrade soils, and a lot of that carbon also moves into the atmosphere. And so that's this vector here. So when we add those up, the current anthropogenic emissions total 6.4 from fossil fuels plus 1.6 from land use change, that's forestry and agriculture, and they all get emitted. That 8 gigatons of carbon gets emitted each year into the atmosphere. These numbers have since increased slightly, and so we're up over 10 gigatons per year at the current time. Anyway, there's our diagram, and on that basis, and on the basis of this diagram, where we have the amounts of carbon in each of the reservoirs, and we have the fluxes, we could also go around and calculate all of the residence times of carbon in each of these reservoirs. And we'll come back to that, but before we do, we're going to take a closer look at how some of the carbon cycle actually works. So if we look at changing atmosphere CO2 concentrations over the last 60 years since they began being measured closely at the Mauna Loa Observatory in Hawaii, you can see this steadily increasing trend of increasing CO2 in the atmosphere. And so when they first started these measurements, the amount of CO2 in the atmosphere was something of the order of 315 parts per million. And that has increased now to this point. This diagram is a little old, but we're now up at 415 parts per million as of this year. And so we can see this trend. So there's two lines here. One is the global average, which is the black line. And then there is the actual measured values at Mauna Loa, which undergo this cycle. So each year we have these peaks and troughs, and this is about 5 or 6 ppm difference. So the actual amount of carbon dioxide in the atmosphere is varying by well over, it's about 1 to 1.5% each year at this particular place in the Northern Hemisphere. So here's a couple of questions for you to think about. And as with the previous lecture, I'd suggest you to pause and think about these questions before moving on. So what indicates the carbon cycle is not in steady state? That should be fairly straightforward for everybody now. This is a slightly bigger question in what is causing CO2 in the atmosphere to trend upward? And what could be producing the seasonal cycle each year that we see over in this diagram here? These relatively large variations every year. Now, I've given you a bit of a clue, and that is, when does the seasonal minimum and maximum occur? And you should note that this is measured at Mauna Loa, which is in Hawaii, and that's in the northern hemisphere. So the beginning of the year, so around about this period here, a little bit after, so this would be January 1. So this is winter, and this would be the northern hemisphere summer here, followed by winter, summer, winter. I think if you look at that, you should be able to convince yourself that during the northern hemisphere summers, which run from about the middle of the year through to this early autumn here, so this would be sort of July, August, September, which would be the warmest months in the northern hemisphere, we have very strong decrease in CO2, and then once we start to get into the colder months, CO2 starts to rise again in the atmosphere. So the question is, what is causing that pattern of behaviour? Any ideas? So let's explore that a little bit further. So here's Mauna Loa. This is where that previous record was taken and where the most complete record is. Since they first started measuring CO2 at the Mauna Loa Observatory, they've set up other observatories around the world, and you can see that the pattern at very high latitude in the northern hemisphere, this is up in northern Alaska, there are these variations here that are approaching 15 ppm per year of CO2 variation on this same seasonal cycle. And so that's about 3 times bigger than the variations we see at Mauna Loa. And then if we move right down to the South Pole, in the southern hemisphere, we see all of those variations, all those wiggles are virtually ironed out, and we have quite a smooth curve that looks like almost like the global average. So why could that be? And why are the variations in the northern hemisphere so much larger than in the southern hemisphere on a seasonal basis? Well, here's the answer. So if we look, it comes down to the northern hemisphere boreal and temperate forests. So in those forests, we have photosynthesis, reduces CO2 or takes CO2 from the atmosphere, combines it with water, and using light energy through photosynthesis produces organic matter. So this molecule here represents organic matter, or a simple carbohydrate, CH2O. And in the process of photosynthesis, we also generate oxygen. The reverse happens when that organic matter breaks down, and this is generally through bacteria chomping up the organic matter, and so we have respiration that oxidizes the organic matter back to CO2. So here we have our carbohydrate molecules, or representative organic matter, combines it with oxygen, and we end up with CO2 being released, plus some water, and also some energy released at the same time. So this energy is used by the bacteria to actually live. And so on an annual cycle, what we have is in the spring and summer months, we have strong photosynthesis, taking CO2 out of the atmosphere and converting it into organic matter. And then after the fall or autumn period, or during the fall and autumn period, we start to get respiration dominating over photosynthesis, and we start to see carbon dioxide being released back into the atmosphere. So you can sort of picture that here. Here we have all this leaf matter on the trees in the height of summer, and then when we come back at the end of winter, all of that leaf matter has fallen to the ground and has been respired by bacteria, which degrade the leaf matter on the ground. And that ends up producing the seasonal cycle in CO2 that we see in the Northern Hemisphere. So why only the Northern Hemisphere, or why so strongly in the Northern Hemisphere? If we have a look at this diagram of the forest distribution around the globe, and you think the key point here is the equator runs through here. So most of the forests are actually located on the landmass that's available at high latitudes in the Northern Hemisphere. So here we have the boreal and the temperate forests at high latitude in the Northern Hemisphere, and they're the forests that end up producing this seasonal cycle in the CO2 signal that we see. That's pretty cool. Now here we have the Carbon Tracker, which is a project run by the US government, where they actually measure carbon dioxide levels in the atmosphere all around the planet using satellites. And as you notice here, I'll just give you a reference point. So we're now coming into summer in the Northern Hemisphere, June and July, and the blue and the pink values are low values of carbon dioxide, whereas the red values are high values. So you can see during the summer and in late summer, the carbon dioxide levels go down to get drawn down very significantly at high latitude by those forests in the Northern Hemisphere. And you can see that in the Southern Hemisphere, we have the reverse happening. So here we have, this is now Northern Hemisphere winter, Southern Hemisphere summer. And during that Northern Hemisphere winter, at the end of the winter, you can see a lot of CO2 being emitted through the respiration of this organic matter by bacteria. There are some other features on this diagram that are worthwhile taking a look at, which really show up nicely. You'll see occasionally, you'll see these very strong emission sources of CO2 in major forested areas. So this is Central Africa. There's also an emission source here that commonly shows up in some of the industrial areas in China. But predominantly what we see is this strong signal of the Northern Hemisphere forests photosynthesizing, and then the respiration that follows in subsequent years. You'll note the influence of the equator, and so we have the divergence of air masses at the, well, we have the convergence and then divergence at the upper levels of the atmosphere at the equator. So there's a very strong distinction between the CO2 behaviour and levels in the Northern Hemisphere relative to the Southern Hemisphere. So that's sort of pretty neat.